All right, guys. Are there any questions from homework stuff that you didn't want to ask earlier for some reason? Anything about homework? You're doing the homework right? It's a really good idea to do it. You know you can come see me in my office, right? A few people are doing that. It's a really smart idea. However you feel about me, I don't know. I think I'm an approachable guy, but maybe I'm not as much as I thought. What's that? Yes, okay. That's what I'm there for. I'll push you in the right direction. I'll give you some. If you haven't gotten very far, I'm not going to tell you too much. I'll give you a little something to start with, and then you can come back and show me what you got. Yeah.
Can you do 14.2 problem 44?
Oh, yeah.
Yeah. You were like, all right. I had somebody come to my office and ask about this. Just got to figure out how to I'll give you a hint without giving the whole thing away. Somebody has done some weirdness here. Hold on. Let's see if it works. Alright, well, it's not your eyesight. It is somebody messing with settings somewhere. 44 in section 14.2? Or
Yeah.
14.2. Yeah, so you've got... If this is the only one giving you trouble, you're doing pretty damn good. Alright, so this is what they give you here. And then they ask you to use the path, investigate this limit as you go to 0, 0. So anytime you have a piecewise function, normally the way that you break some theorems, you make the results not true, is to have a piecewise function do some weirdness. Piecewise functions are inherently strange. That's why I don't like the absolute value function, because it's a hidden piecewise function. To be honest, I don't know if you ever heard a math teacher say they don't like the absolute value function. Well, maybe I'm the first. And then it says, use this path here to investigate the limit that limit. Alright. That'll at least help me out. I've got to reboot that bad boy. See if that does something for him. What's funny to me is, now they tell you right here that A's got to be between 0 and 4. And I think that's doesn't really matter. Yeah, it's not inclusive. I'm going to give you this one little hint that I didn't give you yet. So one little hint, and somehow this plays in. Which one of these is bigger?
If it's greater than 1.
The right answer is depends. The right answer could be you haven't given me enough information, teacher man. The hell's up with that shit? Or you don't have to use those words, exactly. Why have I not given you enough information? Because certainly 2 cubed is smaller than 2 to the 4th, and 3 cubed is even smaller than 3 to the 4th. But what's 1 cubed and 1 to the 4th? They are... Holy crap. And then past that, they invert. Of course, when you multiply things that are smaller than 1, they get smaller. So if you do it multiple more times, they're going to get even smaller. So for 0 less than x less than 1, this is what's true. This will be bigger. Because we normally don't think about between 0 and 1 when we think about what's bigger and what's smaller. You guys kind of, somehow, I don't know if that's the only, that might be the only thing I want to tell you. Somehow that will play into this. So they ask you this path, where a is between 0 and 4, and a is the power, the exponent on the x. Yes?
What exactly are we doing? Trying to find the limit
Yeah, trying to find, investigating this,
in that path.
using this path. Exactly.
Got it.
I like it. All right, so if you haven't tried this problem at all yet, and I love it when I get the looks in your faces like, well, that was a great hint. Thanks, there. But think about, in the context of the problem, what's happening. If you let y be this, then which one are you in? That's really what you're considering, right? And they're saying, actually, they actually tell you what this limit is. They say, prove that the limit is 0, don't they? Am I remembering that right? Yes. So somehow you end up here. Not here. If you ended up here, then it would be 1. Like, I got it. Inspiration. I like that. That's so if y is this, then how does this compare to x to the 4th, for example? And where are you going? You're going to 0, right? So am I going to consider an x value of 28 million? That's silly. I'm going to consider x values that are near 0, right? And what we just say is true for values of x that are near 0, this situation, right? And what's the largest a could be? Not quite 4, not quite 4. So this situation is true. Even if it's 3.999999999. All right, that's enough. That's all I'm going to say about that one. I like that problem. There's a slightly different way to do it, but they both basically hinge on this idea. It's a very much more direct way to do this using that idea. Okay. Anything else from homework that I can barely help you with? Yes? 14.1 number?
Number
42.
42.
Let's see if this. All right, cool. Back to normal. This one here?
Yeah.
All right, so they give us a contour map. So let's talk about what this means. Where are you? There you are. So they ask us, they say a contour map is given. Give a rough sketch of F. What is this? What do these numbers on the side of this thing mean? What does this mean? Yeah, in fact, in this case, remember, we've made this a little more specific than we were doing traces before. Traces could have been in any plane. Now we're considering f of x, y. So what's the, what does this really mean? And be very specific.
The z coordinate?
The z for any of these x, y inputs. So they're giving me, this is the domain. This is where the domain elements could come from, is the xy plane. And they're telling me for any pair of, any coordinates along this, the output's going to be 8. So what is this thing going to look like? What does it mean that these lines are really close together here, but they're not nearly as close together here? Here, what's happening?
Steeper.
It's steeper. It's growing faster. I love it. Which only kind of makes sense, because these are like actual steps, right? If they're these big-ass steps, all right, and then all of a sudden, it's like, you're going up a lot faster than you were before. So that's what's happening here. Okay, and of course, let's see, 8. Then you can kind of count back. I think this goes by 2s, right? -4, -2, 0, 2, 4, 6, 8. Yay! All right. So what's true over here? This part, if I pulled it up, this part, of course, is at 8. So let's say the z-axis is coming out at us, which it would be. All right, and so then it's at. So it looks like this hovering above that. And then as you move towards the origin, what's happening to this? As you move towards the origin, it's getting closer and closer. In fact, where was 0, -4, -2, 0? Right here, this is the actual where it is in the xy plane, because that's for k equals 0. That's when the output is 0. Now, I'm not saying it's easy to graph in 3 dimensions. Hopefully, some of you guys have done the Google search for 3D graph paper, like what I gave you on that last test. It makes it a lot easier to graph those points. So the first thing I would look for if I was a student in a 3D freaking graphing class is look for some way to help me graph 3D. And what's happening as it gets below, so up here it's at 8, then it goes, so it's at 8, then it comes, then it's lower, 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 goes through the origin here, I mean not the origin, but it goes through the xy plane here. Then here it is below the xy plane. And it looks like the slope, how quickly it's going down from there is decreasing. It's less and less slope as you get below the xy axis, xy plane. Okay. May. Okay. Yes. Did you look at the examples they gave you? Did you look at the examples they give you? Contour map, and then they give you the actual image? Do your best. Yes, and you can describe to me what's happening if you want to, but you do your best. I would start with a little paragraph telling me what's happening, or like a few lines, so that if your graph doesn't come out beautiful, I don't need your graph to be beautiful. I know it's painful sometimes, but it really connects you with what's going on three-dimensionally. I don't care however ugly it is. So I can't draw worth crap, but if you tell me go graph that building, I'm going to get to know the building pretty well. My picture's going to look disgusting, but I'm going to know the building pretty well because I'm going to be looking at it a lot more than I ever did. Does that make sense? So when you do this, you're thinking about it more than you ever would otherwise. I don't need it to be perfect. You can describe to me the way it's supposed to look. Get the 3D graph paper. You can even graph some points. Right? You can estimate what that point is and then go up 8 on the 3D graph paper because the output along this whole line is 8. And then the output along this whole curve here is 4. So it's 8, 6, 4, 2. Okay, maybe. Okay, anything else from homework? I think we got into section, oh, sorry. 60. 60? 60. Okay. 68. Oh, okay. This one just says. So notice. So you have level curves. What are level curves? How many dimensions do level curves do we force them to live in? 2. Do you guys see that? All the level curves are on the XY plane. Does that kind of make sense? So if I ask you to describe the shape of the level curves of this surface, what would you say? What do they all look like? Parabolas. That's what I would say too. Because that's what they look like. You can say happy faces, whatever. Whatever that idea is. I like it. So what do you think this function, let's see, 68, right? I like it. Oh, that's gross. So now, at the end of almost every section, there's always a reference to higher dimensional analysis. I don't know if you've noticed that, if you've been reading the book at all. Very often we'll use colors to represent other dimensions because there's only so far you can think physically. Yes, sir?
If you tried to get level curves out of that, would you get level 3D, like blobby things? That would
Sure, blobby things. Sure.
That would
Be more
be-
specific.
That would
So,
be an ellipsoid of some kind.
what was this K? This K, where do I put that K?
Z.
In place of Z. I like it. So you're going to let Z equal some number. You can even do that for yourself if you want to, and then replace it with K. But these are all going to look like this equal to a constant. Now what is this the equation of?
One of the sphere.
Yeah. A sphere radius
3.
3.
So that's
I like it.
ellipsoid.
Yeah, exactly. So anytime I change the coefficients of my any of my variables, I'm going at different amounts in that direction, right? Therefore, this is going to be an ellipsoid. I love it. Every level curve here is going to be an ellipsoid. What's got to be true about K, though?
A hyperellipsoid.
Exactly. But be careful. Yeah, this doesn't ask you anything about what does this actually look like,
Sure.
right? But you can imagine it would be a hyperellipsoid, like a cube and a hypercube. For truly four-dimensional, we're not. You don't have to draw 4D. You're like, dude, I can't do 3D. What the hell is this shit? I want you guys with me. Do you guys see? So if I do make this K, anything you want to, equals K. Any constant you want, except of course that constant needs to be at least 0, right? So the one trivial case would be where all these are 0. So it's just the origin, right? So I'm going to consider K greater than 0, so I can make it a family of things. So if it was this, that would just be a family of spheres of radius rad K. Now it's a family of ellipsoids. I love it. Sounds like some 80s cartoon. Maybe just me. Probably just me. Okay. But don't. The nice thing is if I'm talking about level surfaces of a 4D object, the level surfaces will be 3-dimensional. So I can still describe them. It's not asking you to describe the 4-dimensional object. That's a bit beyond us. That's a bit beyond most people. I like it. All right. Okay. Anything else before I get back? I think we're in 14.3. So let's catch up on what we did before. All right, so if you weren't here last time, you won't be able to answer this question necessarily, unless you read the book. What does this mean, this notation here? What's it mean? And you can give me an alternate notation for it, or you can try to tell me. All right, I like it. So in words, it's the partial derivative of f with respect to. So another way to write this is the partial, so it's not a full d, it's just the partial df dx or dz dx. Is that cool? You see those kind of interchanged in the book if you're looking through the book, because f is z, so what the hell? So then fy would mean the same thing. Now, can somebody tell me less symbolically, more idea-wise, what does that mean? Or
Y constant can take the derivative.
yeah, good. So the process is you leave y constant. You treat y like it's a constant, and you take the derivative with respect to x only. So the y would be a constant. So let's do just a quick nuts and bolts. So if I gave you this, what would fx be?
9x squared minus 7y.
Yeah, it'd be 9x squared
Minus 7y.
minus 7y. I love it. Because you're treating y as the constant, so it's just like it was 2 or something. If I leave y constant and I let x vary, what does that mean visually?
Plane.
Yes. So that's why I got this picture up here. This is a pretty decent picture in your book. page 956. So see here, we've got things oriented kind of strange, but here I'm letting y stay 1. And I can take the derivative with respect to x as I move along the x direction. I'm letting x change. So this is specifically at the point 1, 1. So at the point 1, 1, the output is up here somewhere for the point 1, 1. So there's the surface. So the point 1, 1 is in here somewhere. Let's see, 1, 1 is like right there, roughly, somewhere in there. You guys, semi with me. So when you go to the point 1, 1, the height, the output is something. I don't know. They didn't tell me what the function was. Let me stop there for a second. So if I'm standing on that point and I'm looking in the x direction, I'm gonna the fx gives you how that is changing. How is that surface changing in that direction?
So it's just the slope of the function on the x-axis relative to the x-axis.
Relative to the x direction. I like it.
Okay.
So it's really nice when they say, okay, y equals 1, that plane, where does it intersect this surface, this blue curve? So if I take y equals 1, that represents leaving y equal to 1, not letting y change. So what part of the surface am I talking about? Just this blue line. So we see that blue line? So that's where that surface meets the plane. So now I'm back into 2D. Really, that thing lives in that plane. I can just kind of look at that plane and say, what's the derivative going to be? Well, it's going to be the good old normal derivative that we're used to. Okay, I like it. So that would be more like at a specific point. You let y stay that point, and then you move along in the x direction. What is the surface doing as you move? Is it going up? Is it going down? I like it. So then fy would be the same idea. What's fy computationally?
3x cubed minus 7x.
If you're treating x as a
Constant.
constant, so the derivative of this would be 0.
Negative 7.
Negative 7x, I like it. I like it. Now, so this is kind of review. I'm pretty sure we did this far last time. Let me ask you this. What the freaking hell would this mean? Just to push it along. Let me give you a little help. This is really the way to look at it. So the second letter you see is the second partial you apply. Let me say that again.
So it's order
Yes.
from left to right.
Yes.
What would that mean? So if you're looking at x, that would be just the rate that x changes, and if you take the partial with respect to y, just after that.
That's really cool. Can you imagine if I'm standing at 1, 1, and I've done fx, so I know what that slope is. If I let y change, it would tell me how much the slope changes as I move along the y-axis. Let me say that again. This is a really cool idea. It's a perfect question to ask me. I think somewhere there's an animation for this later. So right now I'm standing at the point 1, 1. There's a certain derivative at that point in the fx, right? What fxy would do is, okay, there's a derivative there. How does that derivative change as I let y change? So if I did this whole thing again and moved over a little bit, or went this way, then the slope might change as I move in the y direction. Yeah, it's like drawing this several times in succession. And then fxy is telling you, well, how quickly is the slope in the x direction changing as I move in the y direction? So you're scanning it through in the y direction, you're saying how quickly is the slope itself changing.
Does this lead into the possibility of having like a t vector with respect, or t with respect to x, and like having?
Yes, we're getting into the chain rule here in a bit. I think that's what you're thinking about.
So it's just like a second derivative, except this second derivative is in respect to x again.
Exactly.
In
The
respect
normal second derivative we're used to in two dimensions can only apply to one variable at a time. So fxy would make no sense in 2 dimensions, right? It only makes sense in 3 dimensions. I like it. So we suddenly have a wider range of second derivatives. So this is still officially, I would call that a second derivative. It's a very specific second derivative. So you can imagine, so what would fxy be? You take the partial with respect to y of fx.
0, -7.
It would be negative 7. And what's fyx? partial with respect to x of fy,
-7.
-7 away. And most of the time, these will be equal to each other, actually. So the order is interchangeable
Usually.
most of the time. Yes, ma'am.
If it wasn't something that easy, if we had like a more difficult equation, the first step would be take the partial with respect to x and then
Totally. So if I ask you what's fxy, if I'm you, I would do this for myself. I go, oh, I need that first, and then I can apply that to what I get. So what about, yes, sir?
Interchangeable most of the time? How do you know?
Yeah.
So it depends on, is it continuous, really, at the point that I'm investigating. If there's any discontinuities in an interval around the point that I'm investigating, then it's not, then it could not be true. Right? These might not agree at that point.
But if it's continuous, then it should be.
Then it should, yeah, exactly. Somewhere they have this. Here we go. Page 959. Oh, yeah. And real quick, before I show you this, oh, so much cool shit we can get into. I know this brings back horrible memories for some of you guys, but do you remember the whole idea of the neighborhood around X? We're not going to suddenly do epsilon delta stuff. Don't freak out. But I like this idea. There's a neighborhood around X and a neighborhood around L, for example. Remember all that stuff? No?
Yeah.
Now see, those of you who remember it, go back and shake the hand of your Calc 1 teacher and say, thanks for talking about that. Because some people will skip it. And that's the rest of you guys going, I don't know what the hell you're talking about. But does that make sense if I said a neighborhood around X? That's a weird way to say it. You think about Mr. Rogers or something. I don't know what you think about. But a neighborhood around X is exactly what you would hope it would be. It has to be close. And the closeness, for those of you who went through this, is defined by delta back then. But we're not going to go there. The whole point I want here is, very often we talk about it just has to be continuous on some interval around X. Or it's got to be differentiable depending on how strong the theorem needs it to be. So in our case, the xy plane is where my inputs come from. So now, if I'm interested in a point AB, it has to be some disk around AB, because now I can go in 2 dimensions, right? So not just a neighborhood like this, but a disk. We call it D. This disk region has got to be continuous on that region. So let me show you. This is on page 959. Just so you understand what this means. Suppose f is defined on a disk D that contains the point AB. If the functions fxy and fyx are both continuous on D, then that's got to be true. The ordering of the way you do the derivatives doesn't matter if that's true. I like it. So the whole idea of a neighborhood and a disk and a region, you can even go a ball around things when you have 4 dimensions. Talk about a sphere circling a input point. Sure, and then you can go beyond that, but let's not. Right. And then here's a little thing about even higher derivatives. Okay. Cool. So here, what would, well, let's talk about this. Yes, sir.
I might be just forgetting that we went over this or something, but how do you prove continuity over this?
Oh, these are going to be functions in their own right.
Okay.
So then you just look at the function that you create and see if it's continuous or not. I like it. On the points on that disk, right? So really you're doing the inverse of that. You're saying, are there any points where this has a problem? Is it in that disk that I want to use?
Okay.
I like it. Yes?
Just to make sure I'm understanding this, the f of y, it's because we're treating x as a constant.
Beautiful.
So it just gets eliminated.
It's used as a constant.
It's
So
used as a constant. So like in that
Yeah.
f of y, it is saying like, 3x cubed is a constant, so it goes to 0, right?
exactly. And why is this negative 7x? Because it was the constant coefficient of y.
Okay.
I love it. You guys see that? Maybe. Okay. I like it. Let that be nice. It's not that big of a step from what we're used to already. It's almost unbelievable it's that easy, actually. Yeah.
So in the geometry of f of x with respect to y, if you took f of x to go to infinity and the f of x with respect to y to go to infinity, it would take the whole graph. Right?
Oh, yeah.
I'm just making sure that I understand that that's what we're getting.
So let's do a concrete thing here for a second. What is f of 1, 2?
Three minus
3 minus
14
14 is
negative 11.
Negative 1. I like. What is fx at 1, 2?
9 minus 14 is 5.
Negative 5. I like it.
Negative 5.
What does that mean if you're standing at the point 1, 2?
The rate of change.
Where's the output at the point 1, 2?
Somewhere.
We know exactly where it is.
-11.
Negative 11. So if I'm at the point 1, 2,
It means x is
my output is negative 11, right? So I bury the treasure 11 feet down below.
What's the slope at 1, 2, negative 11? It's 35.
If I look in the x direction, am I going up or down?
Damn.
Down. I'm going down even more, right? So let's see. If I take... Now remember, the minute I get away from this point, is this still true? Do you understand what I mean?
No.
When is this slope idea true? Only at this point. The minute I move away from that point, this is not going to be the same because it's curvy. But let's just see. So supposedly if I take one step in the x direction, then my output should go down roughly 5, right? So let's take a step in the x direction. One step in the x direction would be, now I'm at the point 2, 2. And why did 2 stay the same? Because fx keeps y constant. Sweet. This is so beautifully concrete. Yes?
Does this represent the not so slow descent into madness that is
Oh,
happening?
sure, yeah.